morning everyone. So today we'll discuss a very important topic from modern algebra, that is groups and subgroups. It is the most basic first chapter of modern algebra, and the whole modern algebra will start building on this only. Important thing about modern algebra is that every topic is interrelated. So this is the first chapter. So if you have a good command over the basic subjects, basic definitions, as I always said in modern algebra, and even in my college days, my teacher also used to say that those who are good in writing, those who practice modern algebra are good in this subject. Okay, so we'll understand the basic definitions and all the important concept from the basic initial. Okay, so I'm assuming that you all must be aware of the concept of sets. Okay, so you have studied sets in class 12. That is a set is a collection of objects you have learned. So you have learned there what is the meaning of set, no need to go there. And there was an important concept, binary operation there. Okay, so we will build our whole lecture over this binary operation. Okay, so what is a binary operation? Okay, so we know that if A comma B belongs to a set, say R, okay, and we define an operation, it could be anything. Here you have to note that whenever we say addition, subtraction, multiplication, moving onward, that could mean different thing. All we mean is an operation. Okay, suppose if I define A operation B by AB upon 6, or I could define A operation B by A plus B upon 3, or I could define A operation B is equal to AB. That's the simple multiplication. Okay, so if for all A comma B belonging to R, A operation B belongs to R, then this operation is called binary operation. Okay, so these things you have learned in your class 12th exam till your class 12th level. That is, an operation is called to be a binary operation, that if it's A in a set, given set, if the A operation B for every A comma B belonging to R also belongs in R. So it is a binary operation. What could be the examples of these operations? We can take operation of addition in the real number. See, we can say that if A comma B belongs to real number, okay, so A plus B also belongs to real number. Okay, so this is a binary operation in real number. Addition is a binary operation, real number. We would also say that A minus B is also belongs to real number. So these are binary. There could be an example which are not binary operation. Suppose we could take the division in the integer. Okay, I would say that consider division operation as division in natural number. Okay, so if 2 comma 3 we know that belongs to natural number, doesn't mean that 2 comma 3, 2 by 3 also belongs to natural number. It is not true. So this division in the natural number isn't a binary operation. Okay, so this is the meaning of binary operation. These things when I have just told you so that you can recall what you have studied in your previous class in the intermediate level. Okay, so moving ahead, the main thing, now we come the definition of group. Okay, so what is a group? See, this is the name of the chapter, group. You will, moving forward, you will study this is a group theory. Moving ahead, in the syllabus there is also ring theory. Okay, then vector space. These are developing over that. See, first you studied set, then you added an operation in it. When you move forward in the ring theory, there will be two operations. When you move in the there you study field, then moving ahead, you will study vector space, which will be defined over a field. Okay, so keeping things very simple, what is the definition of a group? A non-empty set. Okay, a non-empty set G together with a binary composition. Together with a binary composition, a set with a composition. A simple set wouldn't be a group. A set with a defined composition, say a star, it is denoted by star here. Sometimes in some books they use this, a circle, that is A operation B. Sometimes they use addition, simple addition for showing operation. Okay, so I was saying that a non-empty set. So every time whenever you have to prove something is a group, usually people tend to forget to show that it is non-empty. So the first step would be, people generally remember these properties, but they do not know the properties of this. So it says that a non-empty set together with a binary composition. Binary composition. I told you what is binary composition. Binary composition is nothing, it is a closure property. In some books we also write it's a closure property. Okay, is said to form a group if it satisfies the following postulates. Okay, if it satisfies the following conditions. Okay, so what can we do here? Okay, in some book you will see four postulates. I'll change the pen here. Okay, so some books you will see 4 postulates. Okay, that is, number 1 is the closure, second is the associativity, third is existence of identity, and fourth is existence of a inverse. Okay, so if the closure property is nothing but it is the same thing, that if A comma B belongs to G, where G is saying, we are saying that G is a group, then A operation B also belongs to G. This is simple binary composition. Here in itself, the definition itself, it says it is a binary composition, so it hasn't written the first as closure. Okay, but in some books or in many of the books you will see that the definition is a non-empty set G together with an operation composition. Star is said to form a group if it satisfies the following postulate. The first postulate would be the closure property. Okay, so that is the whole thing, that the closure property is shown there. Okay, but in this case it is already written a binary operation, so it's this itself says that it is a binary operation, so it will have the property of closure in it. Okay, moving on to second property, that is associativity. Okay, associative is nothing but it says that if A comma B comma C all belongs to G, then A operation B operation C is equal to A operation B operation C. Okay, so this is associative. Okay, now the third property is, it is the existence of an identity. Okay, existence of an identity. So what is an identity? Identity, there exists an element E such that A operation E and E operation A is equal to A. Okay, that is, there exists and be denoted by E. Okay, identity element is denoted by E. Okay, so if for every A belonging to G, A operation E is equal to E operation A. Okay, so we say that it is an existence of identity. And the fourth property is existence of inverse. It says that for every element A, A. There exists another element, but we write it like A inverse. Okay, in some book you can also see B, doesn't matter what we denote it. It says that there exists an inverse A inverse, that is A into A operation, A inverse is equal to E, is equal to A inverse operation E. Okay, here it is denoted by, here it is denoted by A dash, A prime. Okay, so A dash or A prime operation A is E, where A is then called the inverse of A. See, identity is of a group. Identity will be common. We will in future we will prove that an identity of a group is unique. Okay, so here, but in this case we see that it is an inverse of A. Okay, A prime is inverse of A. For any other element B, then another B prime. Okay, so if these four properties, that is a closure, associativity, existence of inverse, and existence of an identity with an operation given in a set, then the set is called the group. Then the set is called the group. Okay, and if it satisfies another property, see, that is the group, definition of group. If it satisfies another property, if it satisfies another property, that is commutative, that is A operation B is equal to B operation A for every A comma B belonging to G, then we tell this group to be an abelian group. Okay, so if the four properties are there to be proved for a set to be called to be a group, but if this fifth property is also satisfied, then those groups are called abelian groups. Okay, if it is for satisfying the commutative property. Okay, so moving ahead, we'll see some of the examples of group. Okay, suppose I say a set that is a set of natural numbers. Okay, integers. Let us take integer that is denoted by Z. Okay, with an operation addition. See, so what are the properties? Can we say that it is a group? Can we say that it is a group? Integer with an operation addition, can we say that it is a group? Yes, we can check it one by one. Firstly, addition. A comma B, if belongs to integer, then the product is also an integer. Their summation is also an integer. Okay, we also know that it is associative property holds here. See, you have associative property holds here. Okay, existence of an identity, that is 0. A plus 0, 0 belongs to a Z. Okay, this is 0 plus A. This is equal to A. And existence of inverse, that is A plus, if we say minus A, or minus A plus A is equal to the identity element. So all the four properties are satisfied, and it is also a non-empty set. I already proved that. I didn't find it necessary to prove in this case, since it is a very simple case of integer. It is a non-empty set. There is an element in a Z. There are many elements, infinite element in group of integer. So it forms a group. Does it form an abelian group? Yes, it forms an abelian group. Addition of two integers are commutative in nature. You can say that 2 plus 3 is equal to 3 plus 2 in the case of integer. So A plus B is equal to B plus A for all A comma B belonging to Z. So it forms an abelian group, that is Z plus. Okay, moving ahead, what about Z? And now if I change that is the multiplication. let us change the operation, the composition as multiplication. Okay, clearly the closure properties hold. Okay, that is a into b will be an integer if a and b are two integers. Okay, associativity does hold, that we can say that a b c is equal to a b c. So associativity hold. Okay, existence of an identity. In the case of multiplication, thus we have an identity element, that is the 1. Okay, that is if we multiply a by 1 or 1 into a, we get a, that is existence of identity. Okay, so what about the inverse? What about the inverse? Thus, in the multiplication of integer, do we have an inverse for every element? Do we have inverse for 2? We have inverse of 2. What do we multiply by 2? So we can get the value 1, that is 1 by 2. But this 1 by 2 does not belongs to z, that is 1 by 2 does not belong to z. So there does not exist an inverse for each and every element, so it doesn't form a group. This okay. Now what about what about if we consider a set real numbers with the multiplication? Yeah, it is closure. Product of two real numbers are real number. Okay, it is associative. It is a basic properties of real number. It has an identity, that is the 1. And now in this case we also have inverse for every element there. For every real number we have the inverse, so that we could get the inverse for every element. Every a belonging to R, we have 1 by a which belongs to real number. For a not equal to 0, we have 1 by a belonging to R, such that a into 1 by R and 1 by a into a is equal to 1, which is the identity element. Thus it forms a group. Okay, so these were the some of the simpler example. Now if we move ahead with some, I would say a little complex example. What about if we consider a set containing the cube root, nth root of unity? Okay, so what is first of all nth root of unity? Okay, so if z to the power n is equal to 1, then z is equal to 1 upon 1 by n. This is the roots of the equation. In the complex number we have the nth root. See, it will have n roots since it is a polynomial of degree n. Okay, so it will have n roots. The one root is, we can clearly see, is the 1. Okay, but it will have n minus 1 other roots also. So this is the nth root of unity. You may have studied while preparing for IIT JEE and advanced in your intermediate level, but it's not basically mentioned in the NCERT books. So I'll tell you this way, that z to the power n equal to 1, then z equal to 1 upon 1. It has, since this is a polynomial, see, this is a polynomial of degree n, so it must be having n root. Okay, so it has n root, that is e to the power 2 pi r upon n, where r is equal to 0, 1, 2, dot 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 n minus 1. Okay, so if you put r equal to 0, we get 1. If we get r equal to 1, 2 pi r. If we put r equal to 1, so going this way only, we get n roots. Okay, so if we consider the set of these root with the operation, that is the multiplication, then we see that it is n It is in fact an abelian group. Okay, so closure property does hold here. Okay, closure property does hold here. If I take two values and we multiply it, then we get the closure property. Okay, we have inverse for each element. Okay, and how to prove this as a group? Okay, if this question comes in, it won't come in your examination, this basic level, but if it comes in the examination, then we have other methods to prove it. Okay, so we will prove that in later case. When we show that this group is cyclic in nature, it is generated by a simple singular element, then it would be easy to show that. Okay, the concept of cyclic group or normal subgroups we will study later. But for now, if we consider this, I showed you this example so that you could understand that not only about reals and natural number, but also some of the complex questions. Okay, so we have some okay, so here comes another definition. I think I am clear with the definition of what do we understand by the group, meaning of group. Okay, so by definition, by order of a group, okay, we mean that number of element in the group and shall denote it by, okay, this is nothing but order of the group. See, in the real number, what would be the order of that group? Real number, that would be infinite, that is an infinite order. Okay, so in the case of this the earlier example, that is the cube root of unity, roots of the unity, nth root of the unity, there it has n roots, so order of that group would be n. Okay, now here is another group, an important group. This is called an quaternion group. Okay, quaternion group, that is if it has 8 elements first of all, and the properties are defined here, that is G is plus minus 1 plus minus I plus minus j plus minus k. Okay, define a product on G by usual multiplication together with, okay, usual multiplication together with, these are the property, that is I square, j square, k square is equal to minus 1. See, this is one of the groups which is very important. Okay, these are some of the, I would say, most famous group which you should be knowing. Okay, that is I square, j square, k square is equal to minus 1 and ij is equal to minus ji equal to k. See, this is similar to the what we study, the cross product in our, that is I j gives k, okay, j and k gives I, okay, and k and I gives j. So if we move in the clockwise direction, we have the same, that is I multiplied by j we get k, we get j multiplied by k we get I, and if k multiplied by I we get j. Okay, in the clock. But if we go anti-clockwise direction, that is j into I we get minus k, I into k we get minus j, and if we get k into j we get I. Okay, and clearly it is not abelian, as I j is not equal to ji. This is known as quaternion group. Okay, a very important group. See, now we have another group here. We have another group here, that is the general linear group. General linear group, that is the set G of all 2 cross 2 matrix of the form A, B, C, D over reals. Over reals. What does it mean by over reals? Over real means this A, B, C, D are real numbers. Okay. If I say over complex numbers, then it will A, B, C could be complex numbers. Over reals, that means A, B, C, D, where it is given a condition AD minus BC is not equal to 0. That is, the determinant of this matrix is not equal to 0. So why it is we have taken not equal to 0? Since if we have taken 0, then we won't be able to find the inverse of this matrix. the basic necessary condition for a matrix to have inverse is such that its determinant should be non-zero. Otherwise it will be a singular matrix and we won't be getting inverse, and for it to form a group we need inverse element. Okay, that is the fourth property. Again, with non-zero determinant forms a non-abelian group. We know that matrix multiplication is not abelian in nature, that if we consider two matrices A and B, this is not necessarily equal to B comma B multiplication in the matrix multiplication. Okay, under matrix multiplication the operation defined here is matrix multiplication is called a general linear group of 2 cross 2 matrix over reals, and it is denoted by GL 2 comma R. Okay, here is general linear, 2 defines the order of the matrix and R is the reals, and what is the operation or the composition defined is the matrix multiplication. Okay, so this gives the idea of general linear group, that is the G is a 2 cross 2 matrix of the form ABCD over reals where AD minus BC is not equal to 0. Since it is not equal to 0, so that I told you if it is 0 then we won't be able to find the determinant of the determinant would be non-zero, and then we won't be able to find the inverse of the matrix. The basic condition for, and the operation is the matrix multiplication, and it is a non-abelian group, and this is called general linear group, and it is denoted by like this only, that is ZL 2 comma R. Okay.